Welcome to Spring LIB.
For this question, we're going to start for the interference maximum of a grating, which is given by the sine of the angle of diffraction, theta, is equal to, we'll call this m1 lambda divided by the distance between the slits, d, or in other words, the separation of the slits, little d. Where here m1 is equal to, we can say m1 is equal to 0, comma, plus or minus 1, comma, plus or minus 2, comma, and so on. Okay? And the diffraction minima, we can say, are given by, we'll say the minimum are given by sine of theta is equal to m2 lambda divided by d, where m2 here can take on the exact same values as m1. So it can also be 0, plus or minus 1, plus or minus 2, and so on. Okay, so for part A, we're told that if, let's start a new page and indicate this as part A. We're told that the distance between the slits, D, is equal to 2 times the width of each slit, capital D. And we're asked to show that if D equals 2D, all even orders are missing. Well, let's go ahead and rearrange that equation of sine theta for maximum for this situation. So we have sine theta is equal to m1 times lambda over little d, but we're saying little d is equal to 2 times the distance, the width of each slit, big D. Okay, so we can just kind of rewrite this. We have m1 over 2 is times lambda over d. So we just kind of separated that up a little bit. Thus, whenever m1 over 2 is an integer, there will be a minimum of the single slit pattern, and the fringes of those which are missing are going to be given by m1 over 2, right? So we have m1 over 2 is equal to, we have 1, comma, 2, comma, 3, comma, and so on. Or in other words, m1 is equal to 2, comma, 4, because 2 times 2 is 4, comma, 3 times 2 is 6, comma, and so on. Therefore, all the even terms are missing. So we can box that in as our solution for part A. And we'll start a new page for the next part, part B, in which it says show that there will be missing orders whenever the distance separating the slits, little d, divided by the width of each slit, big D, is equal to m1 over m2. Well, if we go back to what we started out with, we have the sine of the angle, theta, is equal to m1 lambda over little d, which is also equal to, from the beginning, we said this is equal to m2 lambda over big D. Rearranging these equations, we find that little d over big D, the lambdas cancel because they're the same in both situations, is equal to m1 over m2. This is what we were asked to show, so we can simply box that in. Okay, and then lastly, part C, where for part C, if we consider, so we can say if the distance between the slits is equal to the width of each slit, then if that's true, then the width of each slit, D, let's rewrite that D to make it look a little nicer. the width of each slit, d, is going to be equal, or excuse me, is going to be much greater than the wavelength that's going through the slits, lambda. Well, if the width of each slit is much greater than lambda, then the diffraction angle, theta, is going to be approximately 0. Or in other words, no diffraction. And you'll just see the image on the screen. So we'll say no diffraction. And that, all of this, can be boxed in as our solution for part C.